So hi everyone, I'm really excited to show you some stuff. It turns out I have only 20 minutes to do this, so I will have to maybe either talk really quickly or leave some stuff out. So I will be talking about my master's thesis, what we've done, and hopefully how we can proceed after this. So this is about signature inference for functional properties discovery. That probably means nothing to you at this point. The subtitle is probably much more relevant to you, how to never write tests manually anymore. Right. Just to jump over the initial motivation section of the talk, I hope we can all agree that writing correct software is hard. If we can all agree, then we can move past this section of the talk and I can just go on. So the way we approach making correct software anyway, even though it's hard, usually involves trading off what language we use. Then we think about maybe we can use formal methods, but that turns out to be expensive. There are a whole bunch of trade-offs to make. But if we assume that we can use testing to make it easier to write correct software, then that's where this is going to come in. The reason why we choose testing as the main point to improve is because that's currently still the most used approach to making correct software in the end. So one of the kinds of testing that we start with is unit testing, which is where we specify one example of an input and an output, and we have to know in advance what it means for our software to be wrong, and then we can check if that's actually not the case, and proceed to have something that is known to not have the mistakes that we think it won't have. So the problem here is that you have to write them, you have to come up with the examples, you have to come up with enough examples so that you exhaust all your code paths. This is annoying, it's not fun, most programmers don't like it. Now, the alternative to unit testing is property-based testing, which we probably already do in Haskell, which is where you specify an entire generalized property of your function. But now you need to know what it means for your code to be correct. You need to describe a mathematical property of your code in order to be able to test it, which is even more annoying. So the first problem that you have to spend the extra time and money to write the tests is even worse than in the case of unit tests, even though now you don't have to write a lot of examples to reach most of your code. So this is already a bit better, but now the cost problem is worse. So if we can ignore the problem of getting the right generators, which is actually not a problem you should ignore, but for the purpose of this task at this talk, we will have to, then the main problem is that we have to come up with these properties. And that's where my thesis comes in. We're going to try to discover the properties of your code based on your code so that you don't have to think about what you want to test anymore. You can just press the button and get suggestions for, is this something you may want to test? Now, this already exists, and there will be a talk about QuickSpec, which is the thing that already exists, tomorrow in the afternoon. You should really have seen the talk before this talk, but that's actually fine. So let's look at the quick example. There is some code. You can ignore most of it. You only have to look at the type signatures. We have a sorting function and a function that can check whether a list is sorted. If we run QuickSpec on it, QuickSpec will say, oh, there are these functions in scope, and here are some properties of it. This is the magic of QuickSpec. You can see how that works tomorrow afternoon. The problem with QuickSpec is, oh, by the way, only the properties from 4 till 9 are probably things you want to put in your test suite to test the functions that we just saw. The first 3, namely that less than or equal to is reflexive, is probably not something you want to put in your test suite to test if a list is, if the sorting function works. So we have to manually pick out which properties are relevant to test. So here's the problem. You have to write a bunch of code in order to run QuickSpec in the first place. So you have to write about double the amount of code than your subject code in order to be able to discover the properties of your subject code. And if you were already too lazy to write tests such that you want to not have to come up with them manually by using property discovery to then make property tests, you're definitely never going to write this code in order to then run something to get your properties. So this is the first problem. There are some other problems, namely that QuickSpec can only work for monomorphic functions because you cannot generate input to parametric functions. The next problem is that QuickSpec is really slow. It tries to find all of the properties of all of your code, which can be really slow. There is some explanation here. We can skip it for this, 20 minutes. So this is where my work starts. We wrote something called EasySpec that is supposed to solve the problems with QuickSpec. The first part is to automate the part of writing this entire piece of code so that you can actually run QuickSpec. And the way we do that is we will try to generate this part of the code. The rest is sort of boilerplate. The input that QuickSpec needs is called a signature, and it contains these functions, which are the functions that are in scope that you want to get the properties about. And it has this background where you can already tell QuickSpec about properties you already know about, so that QuickSpec can then do some optimizations and also not rediscover those properties. And then the main QuickSpec function is of type signature to IO signature, which is where it will find the properties of all of your functions and then put them in the background field of the signature. And the reason this is the way it works is because then you can combine the results of multiple QuickSpec runs sequentially. So the way we generate this signature, we actually have to generate code that will evaluate to a signature that QuickSpec can use. The way we do that is we look at the functions in scope with the GHC API. There are some parameters in there, but you cannot have function types with parameters, so we have to monomorphize this. There is a lot of complicated stuff behind this, but in practice, we uppercase the variables. Then we give it a name. We can also get that from the GHC API. We put them together in this signature. Then we have an expression that represents a signature that we can give to QuickSpec. Now, the current situation after this automation is that we can have this little piece of code where there are only two functions in scope, namely the reverse function and the sort function. We can press a button, or rather run a command, and we get the signature, the properties automatically. So no need to write this code to run QuickSpec anymore. The problem now, and now we can actually measure how slow this is, this has an I'm not going to say anything specific, terrible complexity. So you can see that if you have 15 functions in your code base, this will take about 5 minutes to run. 100 seconds. It's long. That's the point. So maybe we can do something better. To explain how we made something better, I have to really go back a bit and say what a property is. Well, the top is what you'll see in the output. But this is actually sugar for two functions that take a list, map to something else, and those two functions are equal. In the more general case, it's two functions from A to B for some A and B where the A can be generated by randomness and the B can be checked for equality. Now, why is this thing slow? It's because there can be many functions in scope, and the maximum size of the properties that we want to discover is you have to specify it in advance, and it plays a big role in how slow QuickSpec will discover the properties. Now, the big idea we had is that we're usually not interested in all of the properties of your entire code base. You're usually interested in the last function you wrote because that's the one you are going to want to test. Or maybe you just want to specify one of the functions you're interested in. But it's usually not all of the properties of all of your code, but just the properties that are relevant to this one function you're interested in. So the idea is to make a smaller signature from the functions that are in scope by choosing only the functions that are relevant to the function we're interested in, and then running QuickSpec on that. Two trivial ways to do this is, the first one is called full background, which means everything is interesting, and empty background, which means nothing except the thing we're interested in is interesting. So the empty background strategy, as we'll start to call it, will only find things like reflexivity. So only properties that relate only to the function that you're interested in. While full background is essentially the same as automating QuickSpec. And you can see that empty background is already a lot quicker. There is actually something in front of my screen. There we go. Is that better or not? Okay. Right. Now, there's a bit of a box plot here that tells you how many relevant function properties you can find with both of these strategies based on a whole bunch of examples that we wrote. And you can see that empty background finds a lot less relevant properties. Relevant properties than full background does, because empty background can only find the properties that are only related to the function you're interested in. But by the way, empty background can only find relevant equations and not the equations that aren't relevant, because every equation must include the function that you're interested in. So we define relevant property as a property that includes the function you're interested in. Then we made something else, something as stupid as we could think of, and it's by looking at the distance between the function you're interested in and the other functions by name. Oh, I have only 5 minutes. Okay. By name. So you're looking to the 5 most similar functions by name and then choosing those to mean these are interesting. Turns out this is fast enough to be practical, not like QuickSpec. It's faster than QuickSpec. It's fast enough to be practical. You find a lot better, a lot more than with empty background, but it's still not great. We did 2 similar things by looking at the implementation, so the distance between the implementations, and then also, sorry, I have to do this rather quickly, and then also the distance between the types. And it turns out these are all fast enough, but they're all not much better than the others. We've also tried some other things, like other kinds of distances. Instead of the Hamming distance, we can choose the edit distance or whatever. We've also tried unioning the previous strategies where you say the 5 most similar by name and the 5 most similar by type. Turns out it wasn't really better. And then the breakthrough was to see that most properties only relate a very small number of functions. And if that's the case, then we can run QuickSpec more than once and union the results. Now I have to go through this really quickly. So if we can combine outputs of multiple runs, then we essentially want to find very small signatures to give to QuickSpec and then combine the results of those. Now how do we find very small signatures? We just take the tuples of where one of the functions is interesting and the other one is in your scope. This is called chunks. Turns out this is still fast enough because it's linear in time, and it finds more stuff. Now, I don't have a lot of time, so I have to go through all the other things we tried. The point is, we made something that is constant time, and it finds more stuff than QuickSpec does already because of the way the properties interact when you union the results. So this is really cool. The problem is it doesn't work in practice. And the reason why I'm coming here to tell you about it is because these are all practical problems. They're not theoretical problems, so we could make it work. The thing is I only have 6 months for my thesis, so I couldn't do it. So I'd be very happy if there's anyone willing to help me out in making this work in practice. Because currently it only really works on examples because of things like the C preprocessor and some scoping problems. And then in the future, we also want to see, can we do it faster? Because we can now do it in seconds and not milliseconds. Can we think of new functions that we can already put in scope that weren't there initially, like constants? For example, if you're interested in a function about numbers, you probably want to include 0. If you're interested in lists, then you probably want to include empty list into the scope, etc. I have to go through this really quickly. Right. And then the other question is, can we apply this to I/O code? We can discover properties of pure functions, and that's really cool, but you cannot really discover properties of functions like get something from the standard input without abstracting over the concept of effects such that the functions you're talking about are pure. So that would be something to look into. We've also not looked into any way to see whether some relevant properties are more useful than others, and it would be nice to be able to classify some properties based on whether they're going to be useful to the programmer. We haven't found a way to do that yet. So that was it. I had to go through this really quickly. I wish I could have told you more about this. I hope it was still interesting. If there are any questions, feel free to go ahead now. Yes?
Could it be possible that it infers properties which are not correct, or which don't make sense?
So if I understand the question correctly, the question is, are there false positives?
Yeah.
Yes, because that's how randomness works. I'm not trying to insult you, that's just, this is the reason why you will get false positives. That's also not such a problem, because as a programmer you still have to think, do I want this property or not? And if it looks like something that is true, but maybe it isn't because of the false positives, then maybe you've made a mistake in your code. Or maybe you can already see, oh, this should be true, so we should test it, even though or this shouldn't be true, so I am not interested. So you definitely have to go through it manually anyway.
Okay.
Yes.
One more, if you put some contradictory property in this background variable, what happens?
Oh, I've never actually tried that. I mean, I probably tried that by accident, but I haven't seen any specific results of that. That's interesting.
So when I run this QuickCheck property discovery, should I add those discovered properties to my tests, or it will be done dynamically every run of tests?
At the moment, you just get textual output that represents the properties. So you definitely have to manually select the properties, but at the moment, you also have to manually copy paste them. Yes.
Okay, so suppose you define a type, which is a monad, but you don't know it's a monad, for example, and then you run the property discovery. Could it discover this type follows the monad laws and say to you, this is a monad?
Yes, exactly. That's not something new that I did, but QuickSpec could already do that. So it can discover monad laws for you if you'd like. I mean, also if you don't like it, it will just do that.
How good is it at finding corner cases, especially like more complicated corner cases than an empty list or zero?
Do you mean corner case properties like this?
Yeah.
So if we disregard the false positives, it will find all of the properties. There is no way around that. I mean, QuickSpec will. EasySpec may leave some stuff out because it may not be relevant. Randomness is really good at generating corner cases, from my experience. So you will more likely not see a property because of some corner case than see a property that isn't true because of some corner case.